Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the 10th series 10th part of the series of CSIR Net Physics June November 2020 paper solution. Okay, so also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so let's get started with first question of the day. Okay. Question number first. Okay, so this is the 10th part of this series of CSIR Net June November 2020 paper solution. Okay, and we are solving part C questions, guys. Okay, so a certain two-dimensional, a certain two-dimensional, two-dimensional, a certain two-dimensional solid. Okay, crystallizes 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 to a square monoatomic lattice monoatomic lattice. Okay, so square monoatomic lattice with lattice constant with lattice constant with lattice constant A. Okay, each atom can contribute each atom can contribute each atom can contribute an integer number of an integer number of free conduction electrons free conduction electrons free conduction electrons, and the minimum number of electrons the minimum number of electrons number of electrons each atom must contribute okay such that the free electron Fermi circle the free electron Fermi circle at zero temperature, at zero temperature encloses the first Briva zone, the first the first Briva zone completely. Okay, so this is the exact pronunciation of this is Brima. Okay, guys, it's a French name, and in India we say Brilliant Zone. It's okay, but the actual pronunciation is Brima. Okay, so the first Brima zone completely is option A, that is 3, option B, that is 1, option C 4, and option D is 2. Okay, so this is the question, guys. Okay, so I'll read the question for you first. Very good question, guys. Okay, a certain two-dimensional solid. Okay, so it's a two-dimensional. So there is a solid. There is a two-dimensional solid. Okay, which is certain. Okay, certainly there is a two-dimensional solid crystallizes to a square monoatomic lattice. Okay, so that two-dimensional solid crystallizes into a square monoatomic lattice. Okay, so okay, and with lattice constant A, whose lattice constant is A. Each atom can contribute an integer number of free electrons. Okay, so each atom can contribute an integer number of free conduction electrons. Okay, the minimum number of electrons each atom must contribute. Okay, the minimum number of electrons each atom must contribute such that the free electron Fermi circle at zero temperature. Okay, so Fermi circle at zero temperature encloses the first Briva zone completely. Okay, so this is the question. I'll explain it by making a diagram, then it will be more clearer to you. Okay, so so I'm going to make it. So this is x-axis and this is a circle. Okay, it's not exactly looking circle, but it's a circle, guys. Okay, consider it. And these are straight lines. Okay, okay. So this is this is I'm making a diagram in first brilliant zone. Okay, in momentum space. So this is kx and this is ky. Okay, and this is the lattice, guys. Okay, this is square, guys. Okay, it is not looking exactly the square, but it is a square, guys. Okay, consider it's a square inside the circle. Okay, so this is first Briva zone. Okay, so this distance is pi by a comma 0 coordinate. Okay, this is minus pi by a comma 0, this is 0 comma pi by a, this distance is pi by a. Okay, and this is minus pi by a, apology, it's 0 comma minus pi by a. Okay, this coordinate 0 comma minus pi by a. Okay, these are the this is the first brilliant zone. Okay, in momentum space, right? And what we need to find? We need to find this is the Fermi circle at zero temperature. Okay. Okay. So we need to find the number of electron, minimum number of electron that must. This is the question, right? We need to find this one. The minimum number of electrons each atom must contribute such that the free electron Fermi circle at zero temperature encloses the first Brillouin zone completely. Okay, so we need to find out the number of electrons. Okay, number of electrons each atom must contribute. Okay, so that this one, the free electron circle at zero temperature encloses the first Brillouin zone completely. Okay, so this is the first Brillouin zone, this one, and this circle will enclose it completely. Okay, that we need to find out the number of minimum electrons which contribute. Okay, from each atom. Okay, so this is the question, guys. Very simple question. So you need to read this question carefully, and then you can easily solve it. Okay. Well, so I'm going to solve it. So this is the figure, guys. So this means, so this circle we need to find out. This is the circle, guys. Okay, and that is a free electron circle at a free electron Fermi circle. Okay, at zero temperature. Okay, so that is enclosing complete first Brillouin zone. Okay, well, so we'll solve it now. So the Brillouin zone, I'll write it. The Brillouin zone of a square lattice Brillouin zone of a square lattice of lattice constant A of lattice constant A is also a square as shown above. Okay, so oh yeah, this is a square, right? So first Brillouin zone is itself a square. Okay, so the Brillouin zone of a square, okay, square of lattice constant A is itself a square, right? This one, square of lattice constant A itself a square. Yeah, this is clearly seen in the figure. Okay, so you need to know this is the first Brillouin zone, guys. Okay, and this is the free electron circle, free electron Fermi circle, which is enclosing completely the first Brillouin zone. Okay, well, so now I'll proceed further. Excuse me, I'm sorry, guys, my apology. Okay, well, so now we'll find radius of Fermi circle in 2-dimension. Okay, this is a two-dimension case. Okay, so we'll find this radius. A radius is kf. Okay, radius of this Fermi circle, free electron Fermi circle. Okay, so radius of this. Okay, so radius of radius of radius of the Fermi circle, radius of the Fermi circle in two dimensions. Radius of the Fermi circle in two dimensions is is we know, right, that is kf is equal to you need to note down, guys. I will also explain these Fermi circle and Brillouin zone in condensed matter physics class, guys, which is already going on. Okay, so it is this formula is in 2D the Fermi radius. Okay, the radius of Fermi circle in two dimension is, this one is 2 pi. I will also tell you the trick how you can memorize all these of Fermi radius, okay, and the Fermi energy and Fermi and the density of the state in the condensed matter physics class. Okay, so this is 2 pi 2 pi n to the power half. Okay, n is the number density, kf is the radius. Okay, so this is equal to 2 pi n to the power half. This is the formula, guys, you need to note down. Okay, important one. Okay, so now okay, so there is a condition, guys, this you need to know and note down. So the Fermi circle the Fermi circle will enclose the first Brillouin zone, the first Brillouin zone, I can write in short BZ. Okay, Brillouin zone completely. Okay, so these are this one. Okay, completely, because this is height, this is pi by a, right, and this is pi by a, and this is going to be if we that we can get that get this by Pythagoras theorem, right? So this one, so the Fermi circle will enclose the first Brillouin zone completely if that radius kf will be equal to, radius of Fermi circle will be equal to root 2 pi upon a, right? How? Because here I can show you this value is pi by a, this value is pi by a, right? This one, this is also pi by a. So this by Pythagoras theorem, this is going to be root pi square upon a square plus pi square upon a square, right? So pi upon a we can take common, so this is going to be root 2, right? So this should be equal to root pi upon 2 pi upon a, root 2 pi upon a. This is that is the radius, right? This is distance, right? This is the radius. Okay, this one, radius of this, right? So radius of this must be equal to this one, root 2 pi upon a. Very important. These points are very important. Okay, I have written in red. Okay, so now it's easy. So kf value is this. Will so these two should be equal, right? So this implies this implies this one, this value 2 pi n to the power half, 2 pi n to the power half equal to root 2 pi upon a. Now n is number density, right? N is number density, and that is equal to n upon a, right? This we know. So this is going to be 2 pi n upon a, for in case of 2D is going to be root 2 pi upon a. Okay, or 2 pi n upon a is going to be, this will go root to the power 1 by 2, right? Root to the power 2 it will be, right? And this is going to be pi square upon a square. This 1 by 2 will go this side, and this will become pi by a to the power 2, right? And means pi square upon a square, right? So from here n is going to be 2 pi n, that is going to be 2 into pi square a square, right? Pi will cancel with pi times and 2 will get cancelled. Okay, so this is going to be 2 pi a square, right? This is a square means area in a square, right? This is a square, 2 pi a square, right? For that lattice a square, and that is going to be a square, right? So a square will get cancelled, a square will also get cancelled, pi will get cancelled. This implies value of n is going to be pi, that is 3.14. Okay, so then n should be integer, right? Therefore the minimum number of electron will be 4. We have, see here, it is confusing, guys. The option there is 3 is also given and 4 is also given. Okay, so and the value is 3.14, guys. It is more than 3, right? So we'll take the maximum integer value. Okay, so it's a 4.3 means we'll take 4, not 3, guys. Okay, so you can, don't take 3 because 3 is not correct answer. 3 is also is given, right? So option C is the correct answer, and then answer is B, because it's a more than 3 means we'll take 4 integer, right? We are going to take 4. Okay, so this means the minimum number of electron each atom must contribute such that the free electron Fermi circle at 0 temperature encloses the first Brima zone completely is 4. Okay, that's a good question, guys. I hope you have understood it, guys. Next question, question number 2. We are going to solve. Okay, question number 2. It's also a good question. A lattice is defined by, it's a good question, guys, is defined by, I have explained this question in in condensed matter physics as well, guys. Okay, so a lattice is defined by unit vectors unit vectors a1 equal to ai cap comma a2 equal to minus a by 2 I cap plus a root 3 by 2 j cap and a3 equal to a k cap. Okay, where k greater than 0 is a constant. Okay, is a constant. The spacing between the spacing between the 110 planes, spacing between the 110 planes of the lattice is, okay, options are option A root 3a by 2, option B is a by 2, Option C is A and option D is root 2A. Okay, so this is the question, guys. Very good question. Okay. So question is, a lattice is defined by unit vectors A equal to this, A2 equal to this, and A3 equal to this. Okay, where A greater equal to 0 is a constant. Okay, the spacing between 110 planes of the lattices. Okay, so you need to find out spacing between 100 plane. Okay, so you need to find this one. You need to find spacing, right? That is, you need to find this one. Okay, guys, just guys, give me 1 minute, guys. There is some issue. Give me 1 minute, and then I will start. Okay. Okay, guys. Okay. Okay, guys. So first we know we have to find that interplanar spacing, right? DHKL. DHKL we need to find up now. First we need to find we need to get to know that which lattice it is. Okay, so we have been given the lattice is defined by the unit vectors this. Okay, so we have given this one. The lattice is defined by unit vectors. So A1 is given, A2 is given, A3 is given, right? So since we have been given, this is very important point, guys. Okay, since we have given, that is, we have given this one, A1 equal to AI cap, and A2 equal to minus A by 2 I cap plus A root 3 by 2 J cap, and A3 equal to AK cap. Okay, A3 equal to AK cap. So that is given. Okay. This is given. Okay, so we can see these are the primitive lattice vector of primitive cell. Okay, of hexagon, closed pack hexagonal structure. Okay, okay, for SCP. So because I have already explained this in my condensed matter physics class. Okay, so these are primitive lattice vector, primitive lattice vectors of primitive cell of SCP, hexagonal closed pack structure. Okay, so this means we need to find the spacing. We need to find the spacing between plane of the of the SCP. Okay, so we need to find this one. We need to find the spacing between 100 plane of the SCP. Okay, SCP lattice. Okay, or hexagon lattice. Okay, so these are the primitive lattice vectors of primitive. I also told you that you need to know note down and memorize these values. Okay, so these are the primitive lattice vectors of primitive cell of SCP. Okay, hexagonal closed pack structure. Okay, so this means we need to find out interplanar spacing for hexagonal lattice. Okay, so this implies the interplanar 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 spacing interplanar spacing interplanar spacing for interplanar spacing for hexagonal interplanar spacing for hexagonal lattice. Okay, hexagonal lattice is, and that formula I already explained and told you in my condensed matter physics class, which is going on at the moment. Okay, so 7 lectures has been completed so far. Okay, and 8th lecture is going, I'll take 8th lecture after this class. Okay, of condensed matter physics. So this is DHKL for, so interplanar spacing, that is DHKL for hexagonal lattice. Okay, that is hexagonal lattice is going to be, this is the hexagonal lattice. Okay, these are the primitive lattice vectors. So I have already told you, this is 1 upon, and I told you very important, and you need to note down. Okay, so that is 4 by 3 h square plus k square plus hk upon a square plus l square upon c square. Okay, this is the formula, guys. Okay, very important formula, you need to note down. This is for hexagon, for hexagonal lattice or SCP structure. Okay, so DHKL is 1 upon root 4 by 3 h square plus k square plus hk upon a square plus l square plus c square, and that we know, right? For cubic structure we know DHKL equal to a upon root h square plus k square plus h square, right? So this value is very important formula, you need to note down, and this is going to be then D100. Okay, that is going to be 1 upon root 4 by 3 into h square, this is 1 square plus 0 square plus 0 square, hk is 0, right? Square upon a square, right? A square is a here. These are the values, right? These are the values. So from here we can get value of a1, mod a1, that is going to be a. Mod a2, mod a1 means this is a, right? And mod a2 square means this, if you solve it, this is also going to be a, guys. Okay, a, and that is b, right? And this is b, and this one, this, for this a3 mod is going to be again a. Okay, that is c. For hexagonal case, a equal to b, guys, right? And that's why we are writing a. Okay, for SCP structure. So value is a, guys. Okay, a1 is, or we can write this. So a1 equal to, or like a1 equal to a, simply a1 equal to a. Okay, and a2 equal to a, and a3 equal to a as well, right? Very simple. We have done mod of this, right? How? I'll show you for this. This is a square upon 4 plus that 3a square upon 4, right? This mod means root. So a square will take common, so this is 1 upon 4 plus 1 upon 4, right? Root. This is going to be 4 upon 4. 4 upon 4 is 1. Root 1 is 1, right? So that's why the value of mod a2 is a. Okay. So value of this is a. So we can write a is given, right? A plus L is 0, guys. So 0 upon c square, right? So this value is going to be 1 upon root 4 by 3 a square, right? A square. This is a square. Yeah, a square, and these values are 0, right? So this value is going to be root 3a. It is in root, right? Root 3a upon 2. Root of 4 equal to 2. Okay. root 3a by 2. Root 3a by 2. So this is the interplanar spacing. Okay. So answer A is the correct. So guys, now you need to understand, because primitive lattice vectors are given, right? And these primitive lattice vectors are the primitive are the these primitive lattice vectors are of primitive cell. Okay, primitive cell of SCP structure, hexagonal closed pack structure, right? And for hexagonal closed pack structure, and DHKL value, that is interplanar spacing value, formula is this one upon root 4 by 3 h square plus k square plus hk upon a square plus l square upon c square. Okay, and for SCP structure we know A equal to B, right? And these are the A1 B1 A B C given, right? A1 A2 and A3 given, right? And value of mod A is A, value of mod A2 is A, and A3 is A. Okay, so that then we'll put the value, and this is C square is 0, guys. L is 0, so this value is going to be root 3 by 2A. Okay, very good question, guys. Solved. Okay. Okay, this Faiz Uddin. Okay, please repeat. Okay, I'm going to repeat it. Okay, so I have already explained in my condensed matter physics. Okay, so these are the primitive lattice of these are the primitive vectors of uh, primitive cell. Okay, primitive cell of hexagonal closed pack structure. Okay, so because these are the these are the primitive lattice vectors of hexagonal closed pack structure, right? So this is that lattice is the given lattice is the lattice is hexagonal SCP lattice. Okay, hexagonal lattice. For hexagonal lattice, the DHKL value, this is interplanar spacing. The formula for interplanar spacing is this. As I'll give example, this one. Like for simple cubic, we know, right? DHKL value is HKL are Miller indices, right? Miller indices given 100 in this question. So DHKL value for simple cubic, we know, right? That is A upon root h square plus k square plus l square, right? In the same way, the Miller interplanar spacing for hexagonal lattice is this: DHKL equal to 1 upon root 4 by 3 h square plus k square plus hk upon a square plus l square by c square, right? Now, now we have to find these are A1, A2, A3 given, right? So A1 we have found mod of A1. Mod of A1 is A, okay, and mod of A2 is A, and mod of A3 is A, right? In hexagonal structure, I have explained. I would suggest you watch my that condensed matter physics class. Okay, in hexagonal case, A equal to B means A1 equal to A2, right? And this is a formula. So so A and B are equal, right? Means A1 and A2 are equal, and that value is A. We have put, and L square HKL means H, this one. Just wait, guys. Okay. Yeah. So now so what we have done, we have just put the values and got the answer. And this is one. So D100 means the values of H is, because Miller indices given, right? This is 100 given, means H value is 1, L value is 0, and sorry, HK value is 0 and L value is 0. So we just have put the value, right? I hope you have understood it. Very simple question. Fayaz, Fayaz. Okay. Next question, guys. Next question is next question is Question number third. Question number third is, this is also very good question. A spacecraft of mass m, a spacecraft of mass m of a spacecraft of mass m equal to 1000 kg has a fully reflecting has a fully reflecting fully has a fully reflecting sail. Okay, that sail reflects that reflects that radiation completely. Okay, reflecting sail that is oriented that is oriented that is oriented that is oriented perpendicular to the that is oriented perpendicular to the direction of the sun, perpendicular to the direction perpendicular to the direction of the sun the sun the sun radiates 10 to the power 26 watt 10 to the power 26 watt and watt of energy. Okay, and has a mass m equal to 10 to the power 30 kg. Okay, 30 kg, ignoring the effect ignoring the effect of the planets effect of the planets effect of the planets effect of the planets for the gravitational pull for the gravitational pull of the sun gravitational pull of the sun to balance. Very good question it is. To balance the radiation pressure the radiation pressure on the sail the area of the sail will be the area of the sail will be okay, a 10 square m, option B 10 to the power 4 m square. Okay, means 10 to the power 4 meter square. Okay, 10 square meter 10 to the power 2 meter square. This is option A, and option C is 10 to the power 8 meter square. This is the unit height. Okay, and option D is 10 to the power 6. Okay, okay. Okay, so this is the question, guys. I'll read it for you. Question is a spacecraft. Okay, so a spacecraft of mass m, whose mass is 1000 kg, has a fully reflecting sail. Okay, it has a fully reflecting sail means it completely reflects the radiation. Okay, that is oriented perpendicular to the direction of sun, which is perpendicular to the direction of sun. Okay, uh, the sun radiates 10 to the power 26 watt of energy, okay, and has a mass 10 to the power 30 kg, ignoring the effects of planets. So we are just ignoring the effects of other planets, okay. For the gravitational pull of the sun, okay, for the gravitational pull of the sun, okay, gravitational force by sun, okay, to balance the radiation pressure on the sail, okay, to balance the radiation pressure on the sail, the area of sail will be, okay. So what should be the area of sail? That the gravitational pull by the sun, right, will balance the radiation pressure, okay, force of radiation pressure, okay. That's what we need to find, and these are the options, okay. Very good question. I'm going to solve it for you, okay. Okay, so I'll make a diagram, then it is going to be more clearer to you, okay. So so this is the sun, guys, okay. This is the sun, okay. This is the sail, okay. This is the sail, which is perpendicular to the direction of sun, okay. This is the radius of this sun, okay, r, and radius, and this spacecraft is moving in this orbit, is moving like this, okay, in this orbit, and the distance of sun is working as a center, okay. Distance, this or the radius of this orbit is r, okay, and the distance, okay, and this is the sail, okay, and which is completely reflecting, okay. So means the radiation, whatever it is falling on it, that is completely getting reflected, okay. This is the sail, okay. So now whatever we have given, we'll write it, okay. So mass is given, that is m is given, m is 10 to the power 3 kg, okay. Mass, small m is given, 10 to the power 3 kg, and the mass of sun, this is the mass of aircraft, okay, mass of aircraft, and mass of sun is given, that is 10 to the power 30 kg, okay. And p, that is power given, right, this one, this one, the sun radiates 10 to the power 6, 20 to the power 10 to the power 26 watt of power, okay. Power given, that is 10 to the power 26 watt, okay. So this is given, guys. Now radiation pressure for fully reflecting surface, we know, right, I have explained in my optics class, right. If surface is completely refracting, then is going to be radiation pressure is going to be 2I upon c, and uh, if the surface is completely observing, means completely observing, right, or completely absorbing, okay, in that case, in complete absorption, complete reflection, the radiation pressure is equal to 2I upon c, and for complete absorption, the radiation pressure is I upon c. That's what I have explained in my optics lecture, guys, when I solve questions, okay. So here you can see that surface of the cell is completely reflecting, means it completely reflects the radiation, right? So this means we'll find this means the radiation pressure for fully reflecting surface, right? The radiation the radiation pressure the for radiation pressure for fully reflecting surface, for fully reflecting radiation pressure for fully reflecting surface radiation pressure for fully reflecting surface is going to be equal to 2I upon C. In case of complete absorption case, the radiation pressure is going to be I upon C, okay, 2I upon C, right? And now we know intensity. I is, we know that is I is power upon area, right? And so that is going to be power is P, right, which is given, that is power is P here, okay, and this is going to be P upon power per area square, right, per area. So this is the area, guys, okay. So this is going to be 4 pi r square, okay, 4 pi r square, this is r, this distance is, okay. So this is 4 pi r square. So power upon area is intensity. Now okay, so now radiation pressure is going to be radiation pressure is going to be radiation pressure is going to be 2I upon C, right? 2I values here we have point. I is P upon 4 pi square, okay. So radiation pressure is going to be 2P upon 4 pi r square C, right? 4 pi r square C. Okay, this one. Okay, so now what we are going to do, this is the radiation pressure, okay, radiation pressure. Now gravitational pull by that sun, right? Gravitational pull formula we know, right? That is gravitational pull is going to be equal to force, right? Gravitational force G_m_m upon r square, right? This one, this this is the mass of spacecraft, right? Spacecraft m, and this is the mass of sun, G_m_m upon the distance between them is r square, right? So this is the gravitational force formula. We know gravitational pull is this, okay. Now force on sail will find, right? Force on sail, this is the radiation pressure. So force exerted by radiation, right? Force on sail, force exerted by radiation on the sail, okay. Force on sail is going to be, that is we have radiation pressure is given, right? So by radiation is going to be force on sail by radiation is going to be radiation pressure pressure into area, right? Radiation pressure into area of the that area of that sail, right? Let suppose area of that sail is A, okay. Let area of sail equal to A, okay. So radial, so we know force equal to pressure into area, right? So the force exerted by radiation on that surface of sail is going to be that radiation pressure into pressure exerted by radiation into area, right? So this is going to be, this value is going to be this is radiation pressure, we know that is 2Pa upon, this is the radiation pressure into A, right? 2Pa upon 4 pi r square, okay? This is r square c, 4 pi r square, okay? This is the force on the sail, right? And that force on the sail is going to be equal to that gravitational pull, okay, to balance it, right? This is the question, guys. See, for the gravitational pull of the sun, okay, this is for the gravitational pull of the sun to balance the radiation pressure on the sail, the area of the sail will be, okay, for balancing this force on sail should be equal to gravitational 2Pa, right? 2Pa, this is going to be equal to gmm upon r square, gmm upon r square. R square is going to be cancelled, okay? 2 will cancel this 2 times, okay? And then value of A is going to be gmm into 2 pi c upon P. P is the power, right? Okay, this P is the power here. It is not pressure, it is a power, okay? So this is going to be, now we'll put the value, simple value of G we know 6.67 into 10 to the power minus 11, right? Into mass of sun is 10 to the power minus 30, 10 to the power 30, not minus 30, 10 to the power 30, 10 to the power 30, and is m is 1000 kg, right? Mass of spacecraft means 10 to the power 3 kg, and 2 pi 2 into 3.14 into c value is 3 into 10 to the power 8, right? Upon power is given that is power is given 10 to the power 26 watt, 10 to the power 26, right? And if you solve it, this value is going to be 1.25. You can calculate it by calculator. It's a very easy calculation. So this is 2.5 into 10 to the power 6 meter square, okay? So this is the answer. So which option is matching, guys? 1.25 into 10 to the power 6. Okay, which option is matching? Option D is matching, right? This one, option D. So only the power of 10 is given, right? Also 10 to the power 6 meter square is the answer, okay? 10 to the power 6. This is the closest answer, right? Well, guys, very good question. Next question we are going to solve. Next question we are going to solve, okay? Next question. Next question is question number 4. It's a good question and simple question, guys, formula based. Question is, just give me 1 minute, guys. So there's some issue. Okay guys, next question we are going to solve. Question number 4. Question number 4 is electric field due to the electric field the electric field the electric field due to electric field due to a uniformly charged a uniformly uniformly charged electric field due to a uniformly infinite line charged infinite line along the z-axis along the z-axis along the z-axis as observed as observed in the rest frame in the rest frame S of the line charge is ER equal to electric field. Okay, ER equal to lambda upon 2 pi epsilon 0 lambda upon 2 pi epsilon 0 lambda upon 2 pi epsilon 0 x I cap plus y j cap plus x square plus y square. Okay, so this is the electric field in the frame M. In a frame M moving with a constant speed v with respect to s along the z direction the electric field E dash the electric field E dash is okay in the following beta equal to P upon C and gamma equal to root 1 minus beta square. Okay, so this is given and options are option A Ex equal to Ex dash equal to Ex and Ey dash equal to Ey. Okay, and option B is E dash that is Ex dash equal to beta gamma Ex and Ey dash equal to beta gamma Ey. Okay, and option C is Ex dash equal to Ex upon gamma and Ey dash equal to Ey upon gamma, and option D is Ex dash equal to Y Ex and Ey dash equal to Y, this gamma, okay, not Y, gamma Ey. Okay, so these are the options, guys. A very good question. Okay, I'll read it for you. The electric field due to uniformly charged infinite line, okay, along the z-axis. Okay, so we have been given the electric field due to uniformly charged infinitely long uniformly charged infinite line, okay, along the z-axis. Okay, so this is the uniformly charged infinite line, okay, which is along the z-axis, okay, as observed in the rest frame S of the line charge. Okay, if we observe that from rest frame of the line charge, we have got the electric field due to uniformly charged infinite line is lambda upon 2 pi epsilon 0 x I cap plus y j cap upon x square plus y square. Okay, this is the electric field given in a frame M. So in a frame M moving with constant speed v. So there is another frame which is moving with constant speed, okay, with respect to S, okay, with respect to S along the z direction, means which is moving along the z direction. Okay, the electric field E dash. We need to find electric field with respect to, because electric field with respect to S is this given, right? Now we need to find electric field with respect to S dash, that M frame we need to find out, and which we have been given the value of beta is V upon C and gamma is root 1 minus beta square. V is the velocity of that M frame which is moving along Z axis with respect to S frame. Okay, right. Well, so very good question, and it's a formula based question, guys, so you can easily solve it. I'll tell you how to solve. Okay, so now is a formula you need to note down, that's all. Okay, so M is moving in Z direction. Okay, since M is moving in Z direction, okay, Z direction, this means, so we need to find E dash, right? E dash means that is component of Ex dash, Ey dash and Ez dash, okay, which makes E dash, right? So since M is moving along Z direction, right? So it means, that implies Ez dash, okay, Ez dash equal to Ez, okay, because it is moving along Z direction. It means the electric field, Z component of electric field, okay, with respect to M dash is equal to Z component of that Z component of electric field, okay, with respect to S dash. Okay, so E dash Z equal to Ez. Okay, and second, this is the number one. Okay, you need to note down. Second is this one, Ex dash. Ex dash is going to be equal to gamma. Very important formula, you need to note down. Ex, okay, Ex minus V is the velocity of that frame M, okay, V By, okay, and similarly Ey dash is equal to gamma Ey minus Ey then plus, okay, plus V, that velocity of M, into Bx. Okay, so these are three formula, guys, you need to note down, because z component of electric field, okay, with respect to m is going to be equal to z component of electric field with respect to s. Okay, so e dash z equal to ez, because that is moving, that frame is moving along the z direction. Okay, and value of ex dash is going to be gamma, okay, gamma ex minus v dy. V is the magnetic field, okay, along y direction. Okay, and ey dash is going to be equal to gamma ey minus v into bx. Okay, and in this case in this case we can see, in this case, so this is the formula you need to note down. Since bx equal to by equal to 0, okay, so value of bx equal to 0 and by equal to 0. Okay, so since bx equal to 0 and by equal to 0, so this means this is going to be 0, that this means ez dash is ez, this is given, and because b and bx and by is z equal to 0, so it means ex dash is going to be gamma ex and ey dash is going to be gamma ey. Okay, so which option is matching, guys? So here you can see option D is matching, right? Only two components are given in the option. Okay, so guys, because these are equal, so this case, this one, ex dash equal to gamma ex and ey dash equal to gamma ey. Ex dash equal to gamma ex. Okay, so you need to note this formula, guys, these three. This is very important. Okay, if you know this formula, you can easily solve this. Okay, in this case, bx and by equal to 0, so that's why these are the values. Okay, okay, guys, so well, I'm going to stop here, and I would like to request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, guys, thank you. Bye now.